but the way we've graphed them was very difficult to determine the shape of the distribution. Everything was just flat, everything was just in a block. So what we actually want to do is talk about a couple of different ways to be able to clean up that graph, okay? So I can actually do a little bit of creative graphing with that same data set and get a lot better picture of what the shape's going to be. A bunch of dots and stacks of 1 or stacks of 2 doesn't really show me much. But if we'll use these two techniques, a stem plot and a histogram, it'll give us a lot better idea of what the true shape of that distribution is. So both of these you should have, I believe you've worked with them, had a little experience before, but we're going to kind of go a little bit more in depth. Stem plot, you may have called it a stem and leaf plot. I like the name stem and leaf plot. We don't refer to that very often, but it does remind you, I think, how to graph it. So the idea behind a stem and leaf plot is you're going to take every single value and break it into a stem and a leaf. So the stem is how we group things, like one branch has a bunch of is in common for a bunch of leaves. All right, so we're going to figure out how to take our data set, we're going to group them together. All right, so if we're looking at this data set, I always like to start with my key on a stem plot. And the key is going to really help me identify how to write my stem, or my stem and my leaf. The stem's probably the tougher part. Most people can get the leaves. Let's just go grab 1 point off of the data set. So over here, let's say we got 163, right? So we got a female that's 163 centimeters. So if I want to do my stem plot and I want to show 163 centimeters, I want it to equal that. Well, it needs to be a stem and a leaf. So the leaf is always going to be the very last digit. So I usually start my explanation of stem and leaf with the leaf. All right, so if I know my leaf needs to be 3, we're just going to break the number at 3. All right, so leaf is the last digit, okay, roughly. Okay, and we're going to look at some examples in class. Those are quotation marks. We'll look at some examples in class where we kind of manipulate the data, or maybe round the data to certain things to get a bunch of ugly numbers into a digit that we can actually stop at. So, but we're using 163 right now. So 3 is the last digit, so it would be the leaf. And then if we work backwards, the stem is whatever's left. So that's the remaining digits. The remaining digits. A little tough to read right there. So the remaining digits would be the 16. So for 163 centimeters, it would read as a 16 on the left side of the bar and then a 3 on the right side of the bar. So that's the way we work a stem and leaf. So we just grab each of our points, each of our values, and we're going to put them up here as a stem and leaf. So the important thing is number line, right? Number lines need to go in order. So once I know how I'm going to break it, if my stems are all going to be 2-digit numbers, let's just take our data set and break them into 2-digit numbers. Or find out what our 2-digit numbers are going to be. So I've got numbers that, well, we can look right here, that were in the 150s, 160s, 170s, 180s. So if I take off that last digit, I'm left with 15s, 16s, 17s, and 18s. So that's going to be my stem. Those are going to be my stems in this case. So 15, 16, 17, 18. Now, what if we didn't have anybody in the 17s? What if we were the 150s, 160s, 180s? It's a number line. You can't have a jump or a gap in a number line and get a really good picture. So we would, just like we talked today, we would put the 17 there and we just wouldn't fill anything in on that row. All right, so we've got our data set, or we've got our stems set to go. Now we can bring in all the values of the data set. So I'm going to start with the values in the 150s. Now, I'm going to use the dot plot to do this because we want this in order. It's a number line, so we need these rows to be in order also. And that'll help us with things that we work on later. Some of our calculations, like we're doing medians and quartiles and things like that. So in my dot plot, I see my first number is 151, followed by 154, then 157, and 159. So 151, that's a 1. 154, that's a 4, then a 7, then a 9. So 1479 is the way this first row is going to look. All right, so 1479. 1479. See how I spaced them? I don't need commas because each leaf is a digit. That's like each leaf is like a dot from the graph. So because it's one digit, that's the same as one dot. I don't need commas to separate them because I know this isn't 14. That's a 1 and a 4 and a 7, 9. It's actually a 151, a 154, a 157, 159. So really what we're graphing here is the 150s in that row. And in this one, 160s, then the 170s, and the 180s. Okay, so let's take a second. Let's get all these keyed in. All right, so now that I've got all the male heights filled in and they're in order, notice how right here I dealt with 165. It occurred twice, so that's why I wrote a 5 twice, because just on top 4, we want every individual represented. Just like on a dot plot, we had 2 dots at 165, right? So there's 2 dots over here at 165. So that means I need 2 values or 2 leaves to represent that 165. All right, so that's going to occur right there. Another thing to make sure, or notice, see how I left this first column lined up and lined up and lined up and lined up? It's just like when I have repeat values, I'm leaving my rows lined up. I want this to look like all of my 150s, say that I have 4 values in the 150s. And then I have 2, 4, 6 values in the 160s. So I want to be able to see which one's taller. Well, if I did some of them bunched together, some of them spread out, I don't really see them. If you're doing that, you're doing it as a list of numbers and not as a list of individuals that are spaced. Each one needs its own space. So all of your first values need to be lined up. All of your second values, your third values, your fourth, fifth, sixth. So when we get it into this form, we start being able to see a little bit better idea of the shape. But we're going to come back and talk to that. All right, so let's talk about these females. I want to do the females on this other side. So if I do 2 stem plots where they share stems and I do one on one side and one on the other, that's actually called a back-to-back stem plot. Okay. So this would be a back-to-back. Because they're going to share the stems. The males are working in this direction, the females are working in that direction. Okay. On the female graph, if we look at the females for the 150s, we can see that we had 52, a couple of 53s, a 56, a few 57s, and a 58. So that's a 2, 3, 3, 7, 8, 8, 9, right? So the way that would work, we're going to work inside out. So 2, 3, 3, 7, 8, 8, 8, 9. Okay? So with that in mind, let's go through, and I want you guys to pause it right here and take a few moments. I want you to finish filling in the 160s, the 170s, the 180s for the females on that back-to-back, so we can actually compare the males and females here in a second. So I'll wait right here for you. All right. Hopefully you were able to get something that looks like the graph I came up with. Now, as you can see on that second row that we just filled in, it got really long because most of our data, or all of our data for the females, was in the 150s and 160s. So there's a whole lot going on right here. But we do get a lot better idea of kind of what's going on with the shape. Maybe it's not as uniform as we thought earlier. Maybe there is a little bit of a peak over here with the males. Maybe there is a little bit of an area that has more values than the other with the females. But this is still kind of difficult to read. Like, I felt like the dot plot was really, really spread out. It was really, really flat. You couldn't get a really good picture of what's going on. I feel like this stem plot right here kind of works in the other direction. I think it's too condensed because now instead of counting by ones, we're now counting by tens. I grouped all of my 150s, all of my 160s, all of my 170s, all of my 180s. where the females had so much packed in the 150s and 160s, you really can't see a good picture. Males, you get a little bit of a picture on, females, you don't. So what we want to do is when things are too tightly packed, when we use just a regular stem plot or back-to-back stem plot, we can actually manipulate and use what we call splitting stems. Splitting stems is where you, instead of using each stem one time, you maybe break it up into equal parts. So maybe I use a stem twice and it doesn't represent all of the 150s, it represents the first half of 150s and second half of 150s. Or I use a stem two times and it represents, 150 and 151 and then 152 and 153. So we can kind of group them. The key is your stems have to be the exact same size. So if I want to compare like things, like on a tree, I can't take a huge branch and compare it to a small branch. I want to compare two branches that are the same size, and then I can look at all the leaves on those two same size branches. Same thing with splitting stems. If I'm going to split stems because I have tightly packed up data, then I need to make sure that the stems represent the same thing. So in this case, I think the best strategy would maybe, let's unpack this a little bit. So we're going to split our stems and use each increment of 10, the 150s or the 160s or the 170s, we're going to use those twice. So what I would actually go with is I don't know why I didn't have my stems in green. Stems are obviously supposed to be green here. So I'm going to use my 15s twice, my 16s twice, my 17s twice, 18s twice. So we end up getting a back-to-back stem plot that looks like this. So while this right here, that 15 represented all the numbers from 150 to 159, right? We think like our interval notation from our algebra classes. This stem right here is only the first half of it. So it's just 150 through 154. 150 through 154. And this second 15 is the other half of it. It's the 155 through 159. So both of them are blocks 5 units wide. So they can hold values of 5 different ones. But now we can break them up. So we can unpack this data a little bit. So dot plot, really flat, didn't get a good picture. Stem plot was way too packed in. Back-to-back stem plot allows us, because we can break increments of 10 into equal 5s, allows us to break things up a little bit more cleanly. All right, so if we were going through this, now we work with the males. 150s, well, there's 151. 154, and then the next one's 157. So it wouldn't go in this interval, it would go in that second interval, the 155 to 159. So that's 157, 150. Now for the females, or sorry, for the males over there, 160s. So we have 162, 163, 165 is on the second. Remember, this is 0 through 4, this is 5 through 9. So you would do 5, 5, 7, 9. Okay. For the 170s, you actually don't have, but you have one right here, right? If this is 0 through 4s, and then the second one's 5 through 9, so that's 0 through 4. So there's a 4, and then 5, 6, 7. Then my 80s, 80 and 84, and then there's 7. So where here, the stem represented any of 0 through 9 digits. Here, they get cut in half because we did 2 stems. If I'd have done 5 stems, they'd have been cut into blocks of 2. And we can get a lot more creative with those numbers. We'll look at some more elaborate stem plots and how they kind of dig into the numbers better. All right, so let's go ahead and knock out the females really quick. Don't knock out the females. You know what I mean? Take care of the female numbers right here. So you have 2, 3, 3, okay, and then we go to 7, 8, 8. All right, so you can see when we did that, and don't forget our key. So we can use the same one. 16/3 equals 163 centimeters. Key is important. It tells us how to read the stem plot. Because this could be a digit, it could be a decimal point, it could be rounded to the nearest hundredth, it could be a lot of stuff. So we got to have the key. All right, but the big thing is with splitting the stems, what we can see is we've unpacked this female data set, so now we actually see our good shape to it, right? We see that most of the data is on the high end and not much data on the low end. So if we're thinking number line, if there's a little bit on the low end, that's on the left side of our graph. So just like we said here, most of our data was on the high end, as we can see there, and then a little bit, it gets fewer and fewer on the low end. So I think our left skew probably was a pretty good indicator of what was going on with that distribution. So that's stem plots. Splitting stems can get us into chunks of 5. Stem plots can get us into chunks of 10. Really good job of taking a dot plot and working with it in a way that allows us to clean up the data. But what if I don't want to work in chunks of 5 or chunks of 10? I need another strategy to be able to get that data. What if I had 100 data points and the smallest value was 151.7 and the largest value was 152.3? Right, that's 6/10. It doesn't really make a lot of sense in that case maybe to do stem plot because there's not a lot of spread in that data set. So I've got to be able to get a lot more selective with how big of an interval. Now, in stem plots, because you're dealing with increments of 10, right? Every time we move one of these, it's a 10. You really need to be working in multiples of 10, or factors of 10 rather. So you're kind of stuck with like 2s and 5s and 10s as far as how many stems you can split into if you need to unpack. Where if we could just pick anything, maybe I want to work in intervals of 3. Maybe I want to work in intervals of 8 or 7 or 2.5 or 3.19. Who knows, whatever the interval might be that best will break up the data set. That's where a histogram comes in. Okay? So a histogram allows you to work with an interval of any size. Any size. You just have to be consistent. So just be consistent in the same graph. So I'm not going to do something like, okay, let's look at an increment of 5, then another increment of 5, then another increment of 5, and then an increment of 10, and then an increment of 15, and an increment of 32. If I've decided 5s are my interval, I got to be with the 5, with the 5, with the 5, with the 5, and so on. So that's the way you want to work in histograms. All right, so let's pick an interval. What does it mean? What does that look like? Well, let's pick an interval, one that we haven't worked with yet. So maybe I feel like doing increments of 5 like we did here, maybe it unpacked the males too much, okay? So maybe I want to get didn't unpack the females enough. Maybe I want to get a little bit smaller increments. Male shape looks really good, but still maybe that's stacked up a little too much. So let's maybe go a little bit smaller increment. All right, let's try to clean this up a little bit more. Let's maybe pick increments of 4. So when I'm going increments, I need a starting point, or when I'm doing histogram, I need a starting point. So I usually like to find something just outside of that very first data set, okay? So if we look at our original data set, the males, male low end was 151, females were 152. So if I want something that works for both 151 and 152, because remember we're going to be comparing these together, let's just pick 150. I think it's a good starting point. It's usually easy to count off of that. So if I go with 150, and then I'm going to go increments of 4. All right, so I got 150, 154, 158, 162, 166, 170, 174, 178, 182, 186, and 190. So I'm going to count my number line by 4. So that's what the big benefit to a histogram. You get to make your number line whatever you want. So it's like a dot plot in that you can number however you want, but it's like a stem plot because we'll get to be able to stack some stuff up. What do we mean by stack some stuff up? Well, let's just count and see. So on the male graph, if I'm looking right through here, I read these intervals as between. So on the left or between. So that 150 to 154, this interval right here actually means 150 up to 154. So if you'll remember with your interval notation that you did in your algebra classes, this is what we call left side inclusive. So 150 would be included in this interval. The right number, 154, is not included in the interval. So 154 is actually the start of the next interval. So that next interval would be from 154 up to 158. So we're now including, when I said bracket, we're including the 154s in this one, but not the 158. You'll see what I mean when we start throwing some points in. All right, so I'm going to make this the first time with like some dots. You don't ever have to do the dots after this. Just this is how I can kind of understand how these bars are made. So we want numbers from 150 to 154. So let's just start at the beginning. So in here I have 151. All right, so that's one number. And then my next value is 154. Well, 154 would not be between 150 and 154. Okay? It's on that right side boundary. Remember I said the left inclusive, not right inclusive. So numbers that are on the right side of the interval actually get pushed to the next interval. That's how 154 goes in. So that's an important thing right there. Values on an interval break get counted to the right. Now I'm going to tell you, that's not a hard and fast rule. That's just what we're going to do, especially right now. We'll come up with we'll encounter some situations later on where maybe we do our histogram to be left side inclusive instead of right side inclusive. But right now we're going to make our stuff We'll come up with some stuff later on where maybe we make our stuff right side inclusive instead of left side inclusive, meaning we count it to the left instead of to the right. But right now what we're doing is, anytime we come up with a value that would go on a dot, would go between two, it's going to get pushed to the right. Okay? So 154 is not between these two. This one goes between 150 up to, but not including. This is 154 up to 158, but not including. All right, so next one we've got 157. Well, that's between those two. So that's my second value. 159, that's between these two. 162, it's on the line, so we're going to count it to the right. 163, it's up here. 165, that's in here. Another 165. 167, that's between 166 and 170. So is 169. 174, it's on the line, so we're going to push it to the right. 175, that one's between 174 and 178. 177, that's also between 174 and 178. Next we have 180. So 180 is between 178 and 182. 184 is between 182 and 186. 187 is right here. Now, when we're doing these, we don't do them with dots. I'll do a quick sketch, maybe with dots, just to tally stuff up. We want to draw these with bars. So your bar is going to end up looking like that. See how it spans. It goes between 150 and 154. So the way we read this, I see a bar, and it tells me that there is one value. See, it has a unit of 1. Okay. Has a value of 1, so it tells me there was one individual that had a height, one male, between 150 and 154. This one's 2 units tall. So that tells me that there were 2 males between 154, 158 centimeters. There was 1 male between 158 and 162. We had 4 males, 1, 2, 3, 4, in that interval. 2 males in that interval. There were none between 170 and 174. We had 3 in that interval, and 1, 1, 1. So you wouldn't draw it with the dots. I just use those to tally. So that's what a histogram looks like. It takes our dot plot and it allows us to really just compress it until it takes on something that has an actual shape to it. But we're compressing it the same, so it's like a scaled compression, okay? We're not just clumping these in more than those. We're actually making all the intervals, all the spacing between the numbers to be the same. Notice how I didn't put the bar over the 158. A lot of times people will make this mistake when they're doing these and say I had 150 and 154, and they'll do the bar looking like that, you know, something like that. That doesn't mean the same thing. This means all of my values were 150 because 150 is the only thing that bar is over. This means all of my values are 154. All right, so that's not how you're going to write. You need to make sure that it goes between the 2 numbers, because that's saying there's this many values between those 2 numbers. That's why we want to be able to read a histogram. All right, so I'm going to pause right here for a second, and I'm going to let you guys finish the, do the histogram for the female graph, and we'll let you check and see what, how it matches up with mine. All right, hopefully you were able to get a graph that looks like mine. All right, so in this female graph, we see same intervals down here because we want to be able to compare the males and females. So we're going to put them on the same number line. And when we look at it, I feel like we got a really good picture. We got 5 bars. I like a histogram that's got 5 or more bars. Like 5 to 8 usually gives a good idea of what the shape is. Well, you can have more than that, but I feel like 5 is kind of a good minimum number to have. So that's kind of can help you figure out how to pick your intervals or the size of your intervals. But if you look again, we had 3 people between 150 and 154. There were 3 of them. That's why the unit is 3 high. And we end up getting this. So I feel like we can get a really, really good picture of what the shape is on these females now, because we've seen it almost consistently. Really dropped off to the low end, the left side of the number, dropped off to the low end, left side of the number line. We can see how it drops off to the low end. So the tail, so it's really high and then it drops off to the left. So I think it's a really good indication that it is left skew. I feel like the guys are probably, we saw it here, kind of a peak towards the middle. Maybe you could say a bimodal, but I don't know if there's enough values to really go there. I feel like you're kind of a really ugly symmetric graph right there. Kind of see it here with the males. Really ugly symmetric. You might be able to justify a right skew if you wanted to. Again, it's an approximation. We aren't going to have, there's not a true right, true wrong on this stuff, as long as you can justify it statistically. So I could justify symmetric because I can see a peak towards the middle and then it kind of tapers off on both ends. I could justify it as right skew because I feel like you got a cluster or a bulk of data and you got a longer tail. It really tails off here on the bottom where it's just 1, 1, 1, 1 on the far right. So you could kind of go any of the ways, just be able to justify it. All right, so that's a histogram. It's meant to take dot plot data and turn it into a much cleaner graph to give us a better idea on that shape. All right. Now, the last thing I want you to do is I want you to write a comparison of these 2 distributions. So when we compare, we use comparative language. We don't just list values. This one is this, this one is this. I want you to use words like more than, less than, instead of, compares to, relates to, contrasts to. All of those different things. Use that comparative language. Talk about how one looks as it relates to the other. So I'm going to give you a couple minutes because that's going to take you a few minutes to kind of write through. I want to see what type of comparison you come up with. The idea, though, is when we compare, make sure you compare the socks. So don't just describe your socks, compare your socks to your neighbor's socks. So compare the socks of the distribution. Talk about how the shapes are related to each other, how the outliers are related, how the centers might be related, or the spreads might be related. All right, so talk about those few things. I'll give you a minute, and then I'll throw my answer up and see what you guys, how it compares to yours. All right, so let's see how your answer compares to the one that I got. All right, so let's look at the answer I came up with, and let's compare it to the one you got. Now, as you can see, this is a very, very detailed answer. This is the type of answer that I'm looking for, and it's expected in a statistics course. We're being very deliberate with our wording, and we're citing a lot of evidence, okay? So as we look at this, we can see that when I compared the socks, I may use a lot of comparative language. So let me read it to you. The distributions of heights for these 14-year-old males and females are very different. So I've started off comparison. So I've identified what distributions we're looking at, male and female heights for 14-year-old females and males. And I'm talking about, okay, they're very different. I'm not going to show a lot of similarity between them. All right, so they're very different. The male distribution is right skew, while the female distribution is left skew, with neither group showing any obvious outliers. So there was a little common ground that neither one had any outliers. But I said, males were here, females were here. That's a difference there. All right, then we get into the real differences. The typical male height is about 5 centimeters higher than the typical female. I didn't tell you what the male and female were. I used that comparative language. I just told you that the males were 5 centimeters more. And I got that from where we looked over here with our typical male heights. We said the center for males was about 166 centimeters. For females was about 161 centimeters. So the reason, that's why I came up with that 5 centimeters higher. The guys on average, if you want to use that for lack of a better word, were taller because they had a higher center. Their distribution is located further to the right than the females are. All right, so we talked about the difference there, and then we talked about the males have almost twice the variability as seen by their spread. The males' data was way more spread out. The women or females were a lot more clustered together. So that's what I mentioned right there. I didn't have to tell you what those spreads were. I just said it was about twice as much. How did I get that twice as much? When we talked about the spread over here, if you'll remember, we said the spread for the males was about 36 centimeters, while the females, the total spread was about 17 centimeters. That's about twice as much. We said that the internal spread was about 2 centimeters for the male, like 2 centimeters between each guy. With the females, it was about 1 centimeter between each female. So that's what we're talking about. That's where you come up with those numbers. I didn't cite those numbers in here. I just told you the relationship. So if I'm asking you to describe a distribution, you're going to tell me those individual pieces like we did there. If I'm asking you to compare distributions, just talk about which one was more, how much more was it. I don't need to cite the actual number. Now, if you wanted to say, if you want to throw that in there, that's not wrong. Okay, but I'm looking for that comparative language. These were 5 centimeters taller than those. Okay, these were twice as variable as those. But if you want to say 5 centimeters taller because these were 161, these were 166, that's fine. You can put that extra stuff in it. Tell me where those numbers came from. But you don't have to have that. I want to see that comparison language when I ask you to compare. All right, so there's a whole lot of stuff that we talked about. There's a lot that goes in, a lot of different ways we can visually organize categorical or quantitative data rather. And so we've got dot plots that we can do it. We've got stem plots that we can do it. We've got histograms that we can do it. All of those can give us a good picture, but the picture is what we care about. Because if I've got the picture, then I can describe the shape, the outlier, the center, and the spread of that distribution. That's really what we want to get to. We want to be able to take a large group of numbers, get it organized into a picture, and then we want to take that picture and get it into a few observations, because those observations are what we can use to describe the whole picture, the whole group that we're talking about. All right, so that's it for just graphically organizing quantitative data, and I will see you in class tomorrow, guys.